In this video, we're going to look at rates of growth. So we say this function here, f of x, is a lot less than g of x if, as x tends to infinity, the ratio of the two heads towards zero. So for example, let's say this function here is x and this function here is x squared. If you look at the ratio of the two, that would be x over x squared. If as x tends to infinity, you can see that this whole thing here heads towards zero, because this will be a lot bigger than this. Well, because this thing here is heading towards zero, then you can say that this function here is a lot bigger than this function. If you look at the graph, if let's say this is x and this is x squared, y equals x looks like this, y equals x squared looks something like this. As x tends to infinity, you can see that this function will be a lot bigger than this function here. Well, if you look at this, as x tends to infinity, if this function here is a lot bigger than this function here, then you can see that this whole thing here will head towards zero. So let me give you some more examples. Let's say p here can be any number above zero. For example, x to the power 3. So we say x to the power 3 will be a lot bigger than natural log of x, and then this thing here will be a lot bigger than this function here as x tends to infinity. So this one here will be, this function here as x tends to infinity will be a lot bigger than this one here as x tends to infinity. Let me give you another example. If you get a graph plotter and plot natural log of x, it will look like this blue line here. Get a graph plotter and plot in the square root of x, it will look like the red line here. Both of them are heading towards infinity as x tends to infinity. They're both climbing towards infinity. But then if you look at the ratio of the two, one divided by the other. Now as x tends to infinity, this thing here, this function here, the square root of x here, will be a lot bigger than this one here. So if you look at this graph here, it is actually heading towards zero. Because it's heading towards zero, then we're seeing this thing here. Because it's heading towards zero, this thing here is bigger than this thing here, so it's heading towards zero. Because this is satisfied, then we can say that this function here is a lot bigger than this function here as x tends to infinity. And we've seen this in the past. This function here, the square root of x here, heads towards what? This square root of x here is a lot bigger than the natural log of x as x tends towards infinity. We've seen this in the past. So if you look at this, let's say x is whenever you see natural log, think of powers. So let's put 10 to the power of 100 into here. So natural log of 10 to the power of 100 would be this. And then put 10 to the power of 100 into here, and then you square root it. That will then give you 10 to the power of 50. And then this block here is roughly 3. Natural log of 10 is roughly 3. 3 times 100, that would be 300. And then this is a massive number here, 10 to the power of 50. So you can see that this here is 300 is very small in comparison to this. So you can see that this whole thing here is heading towards zero. Because it's heading towards zero, you can see that this is a lot bigger than this. So we can say the square root of x is a lot bigger than the natural log of x. Okay, so if this is satisfied, then you can say that this function will be a lot bigger than this function here as x tends to infinity. So another example, and we've seen this in the past, this function here will always be bigger than this function here for any p greater than 0. Because let's say this p here is 7. So x to the power of 7 versus e to the power of x. Well, as x tends to infinity, this thing here is going to be infinity, this thing here is infinity, you've got infinity over infinity, you can use L'Hopital's rule. So differentiate this, that will then give you this, differentiate this, it remains the same. And then here you check it again, as x tends to infinity, you're going to get infinity over infinity. So you can apply L'Hopital's rule again, differentiate this, it will then give you this. Differentiate this, it will then give you this. You can see that it always, the denominator always stays the same. And if you continue the process, this will eventually become a constant. It will become a constant, and then you can see that this will be a lot bigger. Okay, I hope you can see that from here. And then for this case here, if you look at this here, this thing here will always be bigger than this. So this is clearly the case where this function is a lot bigger than this function as x tends to 0. Because if you look at the two bubbles here, this bubble here will always be bigger than this bubble. So you can say that this is a lot bigger than this. Okay.